Okay, so hi. Yes, I'm Stuart Mumford. I wear a few hats in my day-to-day life. I'm actually here to talk to you about the hat that pays me, which is quite nice. If you want the slides, that's the link to the slides. I'm going to not talk a huge amount about DKIST as a project. I'm mostly going to talk about the technical stuff I've been doing with the calibrated data products and the Python user tools over the last 8 months. Partly that's because that's what I know better, and also because I'm such a lapsed solar physicist that I don't really know what the telescope is anymore. So apart from the fact that it's quite large, it's a 4-meter telescope. It's the first 4-meter solar telescope. Fun fact is that that's about 12 kilowatts of solar power hitting the primary mirror. So that is plenty of photons. This is why we have a time dimension. There are going to be 5 first light instruments on DKIST, and the telescope's being run in a proposal mode where you will propose for an observation, and the telescope will execute that proposal for you, and you will later download the calibrated data products from the data center. So it's a ground-based telescope that's being operated quite a lot like a space-based one. And it is so far on track to go operational sometime early 2020. There is quite a lot of data. With many photons comes many data. We're expecting by the time that the commissioning phase and everything is up and running properly to be getting about 3 petabytes of raw data sent across the Pacific a year, where it will then be stored and calibrated. So there'll be even more than 3 petabytes of data once it's been calibrated, although the exact ratios of calibrated to raw data are unknown. Just as a quick bit of background, I made this excellently informative diagram, so the data center is who I work for, and they're based in Boulder, in Colorado. So the raw data will be sent off the summit and through a large pipe of internet into the data center in Boulder, where in this cloud section in the middle of this diagram, some kind of miracle occurs and the data is calibrated. And then it will be served to users, and science will happen at the end. I have been focusing on the post-calibration or post-miracle side of the thing. I'm making jokes about the calibration because it's the part of this that we have the least understanding of so far. But, oops. What is happening? Okay, so there are 5 instruments, as I mentioned before. There's a broadband imager called VBI. There are 2 scanning slit spectrographs called VISP and cryo-NIRSP. The difference being that cryo-NIRSP is in a liquid helium fridge, I think. And there's a Fabry-Perot interferometer called VTF, and there is an IFU called DL-NIRSP. Once the data is calibrated, all of these boil down to some combination of Stokes, wavelength, time, space, and space dimensions. But that can be any combination of time, space, space, all the way through to Stokes, time, space, space, and wavelength, in that order. A common way in previous instruments of all these types is that the data is used by scientists in the form of various high-dimensional cubes or collections thereof, which I'll come back to in a minute. So the goals of what I've been doing over the last little while is to try and make the calibrated data products that we provide from the data center as usable as possible to people, while also minimizing working within the constraints of the design of the data center. So the biggest thing that we originally were thinking we probably would have in the data center, and we don't at the moment, is any post-processing of the data post-calibration. So once the data is calibrated, it's stored in the big object store set of disks in the data center, and when the users download that data, they're just getting it straight off disk and straight to their computers. We're not doing any kind of post-processing, like making it back into a cube or changing the cube or anything once the data has already been calibrated and put in the store, which is the biggest challenge that I've had to work around. So what we're doing to make sure that we don't have to reprocess the data either on query or when something changes is we're going to be storing each calibrated exposure of each of the instruments in its own FITS file in the data center. So what we actually have is a lot of these wafer-thin FITS files with one frame of a larger hypercube in it stored in the data center. But what we actually want is people want a cube of data so that they can like do their science, except it's in 5 dimensions and not 3, and I didn't try and make a 5-dimensional picture. So this poses some challenges for the user tools, right? Have these data sets can be very large. They can be like maybe 10, 20,000 FITS files in a data set. So having all of those open at once is impractical. Trying to read all of that header information to work out how you want to stitch that cube back together is also reasonably impractical. And basically, what you want to do is minimize the amount of open files you have at any one time so that you can not make your computer melt. So what I discovered, and I'm now going to demo, is a package called Dask. Has anybody heard of Dask? Who's heard of Dask? Not bad, okay. Dask is very cool. I have to say that I haven't gone very far into Dask. I've discovered the array class in Dask and fallen in love with it and used it for my stuff, but I haven't really looked into the other sides of Dask, but it's definitely worth a read. So what I'm doing is the Dask array class allows you to construct arrays from pretty much any Python object that has a shape, a dtype, and a getItem method. So what I'm doing here is creating a class that wraps a FITS file. So when you slice this object, it opens the FITS file for you, slices the data, and returns the data for you, and then closes the file again. What this lets you do is you can stack these objects together with Dask. So I have 10 files in a list called file names, and I construct one of these wrappers and then build a Dask array and stack it all together. And the output is a 10 by 4K image. And constructing this Dask array and doing various operations on it, like multiplication or slicing, has opened none of the FITS files underneath the array at all. So we can multiply by, do arithmetic operations, apply NumPy operations to them or other files to these arrays, and never actually have to open a file at all until you actually need the numbers for something, right? You can press compute, and it will go in and open the one FITS file that this slice requires it to open and read the little bit of data out of it and return it to you. Obviously, if you plot it or similar, it will do the same thing. It will call compute on the bit that the FITS files that you're plotting. So this is what I'm using underneath to abstract away the FITS files from the users and provide them with a higher dimensional array of many FITS files and not have to open them all at once. But the problem is, how do I send the user this Dask array, right? If you've got a long list of 10,000 FITS files, but actually that's a 3-dimensional array of FITS files, right? If you're getting a 5-dimensional array out, you've got 2-dimensional arrays in your FITS files, then you've got a 3-dimensional nested list of file names to construct a 5-dimensional array. And then, of course, we're supposed to be doing science on this, so we probably want some coordinate information about what it is that we're looking at and what wavelength it is and what time it was taken and other things. So as well as having this higher dimensional Dask array, I want a WCS object to be able to do coordinate transformations from the pixel space in the Dask array to actual physical coordinates. So what I ended up using was ASDIF, which is really nice to work with as a developer, by the way. It's a very nice, very simple to use and very Pythonic file format. And what I added to asdiff was this concept of an external array, which holds a reference to a file name. It holds the shape and the data type, and in this case, the HDU number for the FITS file. So I have a nested list of these external array references in the Dask file, which tells Dask everything it needs to know to reconstruct its array. So it has all of the file names are relative, and it knows how big and everything is. And then I build a GWCS object to represent the WCS for the whole Dask array, which will also serialize to the asdiff file. So this is how we're, just quickly go back over this. We're setting up the calibrated data products from the data center come with each frame in a FITS file, and then a higher dimensional cube, which is many frames. And we have a Dask array and a WCS object, which we can build and carry around without ever having to open one of the FITS files. So that's all well and good, but we still need to provide the user with a nice way of opening this and using it. And that's where the ND-Cube work that Danny's been doing and ND data comes in. Despite the fact that ND-Cube currently doesn't support GWCS, I'm working on the same interface of ND-Cube, but without actually using the ND-Cube code that Danny's written so far. It's a nice abstract base class, and that's about it. But the plan is hopefully to unify the two WCS implementations a little bit in both AstroPy and ND-Cube. The idea of this tool is to provide like a simple way to build these objects from the file, from the data set, and to be able to do slicing operations like Danny demoed anyone in the unconference yesterday, where you slice the ND-Cube object and you slice both the array and the WCS. So you through all the operations, you carry around both the coordinate information and the data, so you can go backwards and forwards between world and pixel coordinates for whatever subarray you've got, and then plotting. So basically what I have is, at the moment, is a construct dataset from directory, which finds an asdiff file in that directory and a bunch of FITS files, and then constructs an array. And it allows you to do things like calculating the world coordinates of the first pixel in the 5D cube, and GWCS gives you back out nice AstroPy objects for all of the coordinate information. I've kind of just covered this already. The idea is hopefully to integrate the FITS and GWCS side of this work and ND-Cube in the future, so that we only have one code base and not two. And then the plan is to use this data structure of these like distributed FITS files to provide various other tools like interactive exploration, and also because you have the asdiff file, which doesn't require any of the FITS files to work. The current plan as of the end of last week is to be able to have the user download just the asdiff file, which they can then be able to construct the dataset object from, and they can see the physical coordinate extents of this array and slice the array and do all the other things without actually having downloaded any of the data onto their computer at all. And then once they've cropped out the little box they want to look at, there'll be like a download me these files, and it will know which files it needs to get to just download that section of the cube, which will hopefully massively reduce the amount of data that people need to actually transfer onto their machines. And obviously we plan to add a search functionality and lots of tutorials and documentation to hopefully encourage large swathes of the Solr community to move into Python so that they can use these data sets and not have to process 10,000 FITS files with their RDL scripts. Yeah, thank you.
Nice, 30 seconds to spare. Oh, I didn't even need to ask for questions.
Crushing it.
But if anyone else has questions, think about them.
Thanks. I'm very talkative today. This looks great. Really exciting. I can't wait for DKIST to come online, partially just to use this stuff. But this seems to be a limitation, or maybe have to rethink the way that we're used to working with this stuff, because one of the first things solar physicists like doing, because they're really used to images and pretty images, is in deciding the region they want, they're going to want to plot and quick look everything. But it sounds like you've got to, in order to get the whole cube and quick look the whole cube and to figure out what part of the region you're looking at, you've still got to download everything.
All the data,
So how are we going to get around that impulse?
Yeah, there will be some browse data that as part of the search interface in the data center, so you won't have to, like, if you do a search through the web interface, you'll be able to see like preview images and movies and stuff, which hopefully will assuage some of that. And I'm also hoping that you'll be able to, once you've got the empty data set, you'd be able to like overplot it on other data you might already have, or like maybe we could do some like reduce the time cadence or other tools to help do quick look. But
in those tools, would you be able to get back like the pixel indices of the region you're interested in, so that you can like just say, oh, I know that I want this region. I sort of export pixel coordinates or something, and I can use it straight into this Dask setup so that I only download what I need.
Probably not from the search interface, but maybe from some of the other tools. So, yeah.
Got a remote question that was asked on Slack. Did DKIST want to hire specifically a software engineer to write their pipeline in Python?
The actual pipeline code is the purview of the people who are building the instruments, so there's a little bit of variation in who's writing that. It is all the ones that are currently in the process of being written are being written in Python. The data center itself just made the decision to use Python, I believe partly motivated by the NSF, and then found me at the end of my PhD and decided that they wanted me to do it. So,
Any other questions? Okay, awesome. Thanks, Stuart, and let's thank all of our speakers for this session.